Okay, so I mean, I want to keep the talk informal, so I suggest, stopping me if I'm going too fast, or unplugging the thing if I'm going too fast, and also just, ask me questions. I'm going to start with a very basic question and motivate the rest of the work. So I will sort of introduce the theory of orbit equivalence, the cost, and then maybe, if I have time, I will mention my result just for the sake of mentioning my result. But the main point of the talk is to expose some, like at least two parts of a very cool theory that I really like. So I want to advertise it. Okay, so let's start with a basic motivating question. I'm going to denote by x mu a standard probability space. That means it's the 0-1 interval with the Lebesgue measure, so isomorphic to this. So we can think of it as this exactly. So x mu is that. Now gamma will always denote a countable discrete group, and Fn will denote the free group on n generators. So here's the question. Let's say I give you two actions of Fn and Fm, like so the free group on n generators and on m generators on the same probability space. And I'm assuming that these actions preserve the measure, so like each element, when you multiply a set by it, that set gets transferred somewhere else, but its measure doesn't change. So it's measure preserving actions. And I'm assuming the action is free, so there are no fixed points. And ergodic, I'll define what it is, but think of it as indecomposable. So these actions are atomic. You can't decompose them. So this is sort of like non-triviality assumptions. Think of it this way. So two non-trivial measure-preserving actions, one of Fn and one of Fm. Now suppose that these actions have the same orbits. What does this mean? That means, so actions induce orbit equivalence relations, right? Being in the same orbit is an equivalence relation. And as such, I'm assuming that these equivalence relations are the same. So the actions might be different, the groups might be different, but the orbit equivalence relations are the same. Now the question is, must it then be that n is equal to m? So must this equivalence relation somehow equivalence relations remember the number of generators of the free group that induced them? So how rigid are these actions, in other words? So this is sort of the rigidity question for free groups. And let me elaborate on this more. So measure-preserving action just means that every measure-preserving action of a group gamma just means that every element of gamma, when you take a whatever set, measurable set you want, when you transport this set by the element of gamma, the resulting set still has the same measure as the initial set. So like, think of rotation of a circle. You just rotate, nothing, no measure changes. Ergodic, okay, so the best way to remember this term is what are transitive actions?
Yes. So those, the F, the blackboard F, N, and Fn, they are subgroups generated from elements from gamma?
No, they are just free groups. What's the relation between
gamma and they're completely independent?
Yeah, there is no gamma. Gamma is just abstract notation for countable.
Okay.
So gamma is equal to Fn and then gamma is equal to Fm.
Okay.
Yeah, yeah. So they're just free groups. The free groups on n and m generators. And so okay, so I'm defining ergodic. And what are transitive actions? Well, transitive actions are those that have one orbit. But the better way to say it for this is transitive actions are those that any invariant set is either everything or nothing, right? So now let's say the same statement measured theoretically. I'm wearing measure theoretic glasses. I don't see null sets. So then what I say is any invariant measurable set is either null or co-null. Is either everything as far as I see or nothing as far as I see. That's the definition of ergodic. And that means you can't decompose them, decompose your space into two positively measured invariant pieces. So atomic actions, okay? And any action admits an ergodic decomposition. So any action can be split into atomic pieces. That's why we study ergodic pieces, because that's where the content is now. All right. So a rigidity, philosophical rigidity question in general, not well posed, of course, is how much of the group is remembered by the orbit equivalence relations of its free ergodic probability measure preserving actions. So I want to preserve a probability measure, so that's why PMP, so we just say PMP actions. And I want the action to be free because if the action has fixed points, then what you see is a quotient of the group and not the group. So you cannot expect the equivalence relation to remember the group if the action already just sees the quotient of it. So that's why this freeness assumption, and ergodic I already mentioned, is the atomic pieces. Okay, so this is a general rigidity question that I find very interesting. You know, you just forget the action, forget all of this equivariance, only keep the orbit equivalence relation, and think of how much information about the group it carries. So let's consider equivalence relations in general to make more sense of this question. All right, so let E be an equivalence relation on X. But, you know, we don't, so what are the conditions on E? What is the regularity assumption on E? So the nicest thing you can assume about E that happens in practice is that E is a subset of X squared, right? It's a set of pairs. So as such, you suppose that you demand that it's a Borel subset of X squared. So Borel is, you know, when you do measure theory, Borel sets are the nicest sets. So you demand this equivalence relation to be Borel. And I also demand that each class is countable. So each equivalence class is countable. The space is, you know, continuum, it's 0, 1. Each class is countable. That means we have a zoo of classes, right? Continuum, many classes. Each class is very nicely combinatorially discrete, but the number of classes is continuum. All right, let's give some examples. This one from analysis. So Vitali, so-called Vitali equivalence relation on the reals. You call two reals Vitali equivalent if their difference is irrational. In other words, this is just the translation action of Q on R, the orbit equivalence relation of the translation action of Q on R. So, of course, every class is countable because Q is countable. Another one is eventual equality on the Cantor space, namely the space of all binary sequences. So you call two binary sequences E0 equivalent if there is some truncation point, the same for both sequences, that when you truncate it, the rest are equal. You can call, again, this equivalence relation is a countable equivalence relation. It's basically you take union over all truncation point, and below the truncation points there are only finitely many various sequences. So tail equivalence is similar to E0, this eventual equality, but now you allow truncation points to be different. So again, it's a countable equivalence relation. So in general, more generally, if you have all orbit equivalence relations that are induced by countable actions, Borel actions of countable groups on 0, 1, they induce the orbit equivalence relation they induce is countable just because the group is countable. And this orbit equivalence relation will be Borel, because to say you are in the same orbit, so X and Y are in the same orbit, you say there exists a group element gamma that's a countable union, such that gamma X equals Y, and that's a Borel relation, if the action is Borel.
Now those first three examples, those are all continuous equivalent, aren't they?
No, these are Borel equivalent, but not continuous.
Okay.
Yeah, all of them are Borel pi-embeddable. All right. So, so this last example I claim is the example. There are no other examples. So this is the theorem by Feldman-Moore. It says that in fact any abstract countable Borel equivalence relation you take can be induced, is induced as the orbit equivalence relation of some countable group. So you give me an equivalence relation, I look at it, I produce an action of a countable group whose orbit equivalence relation is exactly what you gave me. This is great because in the same orbit, it allows for points to name each other. in a Borel fashion. So like if you fix a point x, then it sees all of the other points in the orbit by just varying the group elements. So it calls it Bob, John, and whatever, and maybe the other elements have different names for different elements, but at least you have a Borel naming system. Okay, so this example is everything. So in general, countable Borel equivalence relations are exactly those arising from countable group actions. All right, now let's introduce measure. So we were sort of describing just Borel actions, but now let's have measure. So if now the equivalence relation is on a measure space, you call it the equivalence relation, ergodic, if, just like before, what did I say for group actions? I said any measurable invariant set is either null or co-null. Here invariant just means union of E-classes, E-equivalence classes. So again, I call an equivalence relation ergodic if any measurable subset that is E invariant is either everything or nothing as far as measure is concerned. Now this is the sort of maybe the unintuitive bit. For a group action, I define measure preserving as every group element, when it acts, preserves the measure. Now I have an equivalence relation, so there's no action. But I want to again define what measure preserving means for an equivalence relation. And here is what I say. Intuitively, I just want to say all elements in the same orbit have the same mass. But mathematically, what I say is that whenever you take any Borel automorphism of your space, so any Borel map from x to x, so it's moves some points to some other points. If this map fixes the classes set-wise, meaning that every element, when you move it by this map, they stay equivalent. So the classes stay put, points move. So this automorphism gamma permutes points within the classes, but does not permute the classes at all. This automorphism, as an automorphism, is measure preserving. So it preserves the measure. When you take a set A, apply gamma to it, what you get has the same measure as the original set you started with. So that's what it means for an equivalence relation to be measure preserving. And you see, when you have a measure preserving action of a group, its orbit equivalence relation is measure preserving. So that's why we're concerned with these equivalence relations, because we're concerned with measure preserving actions of groups. So now basically the important definition is how do we define isomorphism of two equivalence relation on two different measure spaces? Well, we say that they are measure isomorphic, and we write it this way. So E measure isomorphic to F. If there is a measure preserving isomorphism, so there is an isomorphism of measure spaces, meaning that when you map a set by F, so it's a bijection, such that when you map a set by F, the image set has the same new measure as the original set has the new measure. Okay, so it's a measure isomorphism of measure spaces, such that for any two equivalent points, for any 2 points in the domain, so here, those 2 points are E equivalent if and only if their images are F equivalent. So that's what isomorphism means, for measure isomorphism for equivalence relations. So basically what it says is up to maybe throwing a null set here and null set there. So this is almost everywhere, right? So you throw null sets, you don't see them. So after you throw null sets, what you have is literally just renaming of elements, that's all. All right, and renaming the equivalence relation. So now, the final definition I want is for group actions. So I call two group actions by different groups. So that this is gamma, this is delta. Two different countable groups, two possibly different measure spaces, and so different actions. I call these two different actions orbit equivalent if, when I look at the orbit equivalence relations they produce, so this E alpha is an orbit equivalence relation here, and E beta is an equivalence relation on Y nu, these orbit equivalence relations are measure isomorphic. So no matter what actions were, the orbit equivalence relations are isomorphic. And what we had before, this question for free groups, was exactly this. If you have two free ergodic probability measure preserving actions of the free group on n generators and on m generators, if they are orbit equivalent, so the same equivalence relation, or up to isomorphism, the same equivalence relation, must it be that n is equal to m? So this is the question I started the talk with, and basically I'm building up to an answer. Not by me, it was answered in 1997. We could ask the same question for z to the n. I mean, after all, we understand this group may be a bit better than f to the n, than fn. So why don't I start with a simpler group like z to the n and ask the same question? If free ergodic probability measure preserving actions of Zn and Zm are orbit equivalent, so have the same equivalence relations, must n be equal n? So unlike the Fn, the free groups, these groups are abelian and hence they are amenable. If you've heard of amenable groups, I mean they are. It's a wonderful class of groups introduced by von Neumann, I think, and those are groups that admit, they apparently have 700 something equivalent definitions. So that means you really have a really good notion in mathematics if it has like 700 something equivalent definitions. So one definition is that those are the groups that admit finitely additive translation invariant probability measure. So you can build one for Z using ultra filters, but anyway, it's irrelevant. So these are groups with measures. Think of it that way. And this word is a pun because the measures are referred to as means. So this is amenable groups. Anyway, so free groups, they are not amenable because they admit a Banach-Tarski type decomposition. Like each free groups has translates. You can rearrange and translate it to obtain two of the same free group. So because of this Banach-Tarski business, you can't have a measure on it because 2 is not equal to 1.
So by that definition of admitting the additive measure, are all locally compact groups amenable?
No.
So our measure doesn't have to be finitely additive?
Probability measure. Our measure on locally compact groups is infinite.
It may not be probability measure. Okay.
Yeah. Compact groups are amenable.
Okay.
Yeah. But these are not compact, right? Like these are very non-compact. So okay, so the Zn and Zm are amenable, free groups aren't, and here is the striking result. It's built on the work of Dye for Z, and then Ornstein-Weiss completed it for amenable groups. It says that in fact any two free ergodic probability measure preserving actions of any two amenable groups are orbit equivalent. So Zn and Zm all the same. So what this says is that the orbit equivalence relation remembers literally nothing, except that the group acting was amenable. So it does not differentiate between Zn and Zm whatsoever. So in other words, up to orbit equivalence, there is only one free ergodic probability measure preserving action of amenable groups. So amenable groups, they have only one action up to orbit equivalence. In particular, the answer is not at all to this question. So n does not have to be equal to m. Okay? However, for non-amenable groups, including the free groups, the picture is very different, dramatically different, and this gives, one of those 700 definitions. This dichotomy. It says that every non-amenable group, it's a wonderful result of Iona and Epstein. It says that every non-amenable group has continuum many non-orbit equivalent free ergodic actions. So amenable have one, non-amenable have continuum many, and that's a characterization of amenable groups. As I said, one of the 700. All right. So this is a result. but it doesn't answer our original question. Sure, now we know that Fn has continuum main non-orbit equivalence action, so does Fm. But what I was asking is, you know, do any two actions that happen to be orbit equivalent, can any two different can an action of Fn and Fm for different n and m be orbit equivalent? That's what I was asking. So let me restate it again. So again, the question is, if three ergodic PMP actions of Fn and Fm are orbit equivalent, must n be equal to m? So in order to distinguish between, so what we're saying again, equivalence relations are the same, do the groups have to be the same? So in order to distinguish between equivalence relations up to measure isomorphism, we will attach an invariant to the equivalence relation called its cost. So this is going to be an interesting invariant. I mean, it's not obvious. Once you come up with it, everything is nice. But, you know, it took Levitt and Gaboriau to come up with this definition. So, colloquially speaking, how much does it cost to describe an equivalence relation to someone? How do you describe an equivalence relation? You have to tell, you have to basically describe what the classes are. So here is the picture, right? We have, these are E classes. Each class is countable, but there are continuum many of them. How do we describe these classes? Well, if you think of E, what is E? E is a set of pairs, right? And you can think of E as set of edges, because it's a set of pairs. So E, what E does is puts an edge between any two elements of each class and no edge between different classes. So E, in fact, is sort of a complete graph on each class. All right, so thinking of it that way, it has a lot of redundancy in it, because, you know, you don't have to have cycles. In order to describe a connected component, you don't need cycles, for example. So thinking of E as a graph, you can aim at describing E by using edges between the points of X to connect each equivalence class. So you want to achieve that each equivalence class, any two points are connected. And that way, you will describe the equivalence relation completely. Just give a graph and say your equivalence relation is in fact the connectedness relation of this graph.
So these classes are pre-specified?
Sorry?
These classes are pre-specified? Or
yeah, classes are pre-specified. I give you the E, I give you the equivalence relation.
Okay.
So you see the classes.
But I was thinking, is there any way that these methods can be used for classification?
Yes, so we're going to get to that.
Okay.
Classification of equivalence relations. So I want to attach.
No, meaning that if I completely mix the data, the classes, then is there any way using this procedure classifying and getting the right class?
What do you mean mix the data?
So here you put them in three classes, right?
Three?
Or four classes.
This is just a picture. I mean, there are continuum many.
Okay.
So if I understand right, the cost so far is you specify continuum many countable graphs.
Yeah, I haven't defined cost yet. This is a contemplation.
Okay.
Yeah.
But this should be sounding enormous to me, right?
Huh? Yes, this is enormous.
Okay.
Yeah, I mean, this is I mean, this is as enormous as E is. Maybe even smaller. E is a set of pairs, right?
Oh, E doesn't bother me. Specifying even one countable graph sounds enormous.
But E is a countable union, a continuum union of countable graphs.
Yes.
This is what I'm trying to say. E, in fact, has all possible edges in its classes, right? E is a complete graph on every class. That's what equivalence relations are. They're complete graphs. Sorry, what's your question again?
Okay.
I want to attach some
The
number.
reason I ask you that this is pre-specified classes or not, so let's put it the other way. If the classes were not pre-specified, can we specify them or not?
Yeah, so if you give me the graph, then I recover the equivalence relation by just saying 2 points are equivalent if they are connected by a path.
Okay.
So if they are in the same connected component of the graph.
Okay.
But I haven't defined cost yet. I'm just saying maybe this is an approach to try to aim to build a graph such that its connectedness relation is exactly E. That's what I'm saying. So now let's define it rigorously. So once again, let E be a countable Borel equivalence relation on a probability space. So we have this picture. A graphing G of E is a Borel graph. By graph I mean is a set of edges. By edge I mean it's a set of pairs. It's a point. It's a pair of points. So a Borel graph is just a subset of x squared. That's Borel. So as a subset of x squared, it's a Borel subset, just like E was. And I want the connectedness equivalence relation to denote that I denote by EG to be exactly E. So this picture, I'm building a Borel graph. So don't think of it as a union of countable, continued union of countable graphs. It's Borel as a structure. It's a Borel graph. I'm building I'm saying a graphing of G is a Borel graph whose connectedness relation is exactly E. So it has, E was complete graph in every connected component, and we're throwing out some edges and getting a G, but still want a Borel graph. So now the cost of G, just a graph, so forget the equivalence relation for a moment. The cost of G is supposed to be the measure of its edges. So if I give you a finite graph, I say that the cost of G is the number of edges. How do we count number of edges for a finite graph? There are two ways to do it. One is to just do 1, 2, 3, 4, 5 count. The other one is to sum up the degrees and divide by 2. Well, summing is good because I can integrate. So the summing thing generalizes. I integrate over the degrees and divide by 2. So this is the quote-unquote number of edges for this graph. So it's a measure of edges, really, without quotes. Okay? So a cost of a graph is just a measure of its edges. Now, how can I possibly define the cost of not a graph, but the equivalence relation? What can I do? So an idea would be to try to build various graphings for this E. So basically, I'm given this equivalence relation. So I want to build a graphing with minimal number of edges so that, when I compute the number of edges, I get a small number. Picture, I have, okay, here's the definition. The cost of the equivalence relation is just the infimum of the costs of all possible Borel graphings. So it's like, I have rooms that I need to be wired in the Borel fashion. So I need like one big wiring so that each room is wired, so it's connected between each other. So what do? I call all, let's say, Borel certified wiring companies, and I get quotes from them, and I take infimum of these quotes. And that's the cost of the equivalence relation.
What is degree? Is it valency of the graph?
Yeah, valency.
Valency, okay.
Mm-hmm. But it's degree of a vertex, so it varies from vertex to vertex.
Is it obvious whether or not the infimum has to be realized?
It's not obvious and false. So
okay, it does not have to be realized.
It does not have to be realized.
It's not obvious that it doesn't have to be.
Yes,
okay.
Yes, nothing is obvious. In fact, I'll just tell you shortly which class of equivalence relations admit the infimum. So not everyone does. Okay, so given an equivalence relation, how on earth am I going to compute its cost? Am I really going to call all these Borel certified wiring companies and get the infimum of the, quotes?
There aren't enough of them.
There are, yes, exactly. But one idea is, what if my equivalence relation had minimal graphing? What would the minimal graphing be? Minimal graphing means if I cannot remove an edge. If I remove an edge, I disconnect the class, which I don't want. So in other words, minimal graphing is, so what are minimal graphings? They are exactly those that don't have cycles. Because if I have a cycle, if I remove an edge, I'm still fine. So a graphing T of, so this is a Borel graphing, right, always. So a graphing T of the equivalence relation E is called a treeing if it is acyclic. And of course we call it a treeing and not a foresting because we think of each equivalence class is a connected tree. So we call it a tree. Now, a question. So, let me define now the class of equivalence relations. So, a treeing is an acyclic graphing of E. Given an E, I call it mu treeable if, after throwing out a null set, I can find a Borel treeing for E. So E is called treeable if it admits a Borel treeing. Now you can say, why can't I put a tree on any equivalence relation? Let's do something, real simple. Sorry if you guys can see. I'll draw one more over there. So these are the continuum many classes, right? I can, use axiom of choice, select a point from each class, and then connect, like these, stars or suns, connect every other point to this pre-selected point. And here, I built a very nice, bushing or treeing, whatever, right? This is a treeing. But guess what? Because these points were chosen, so this set of points was spit out by axiom of choice, it's complete garbage, not Borel, not measurable, nothing. So this graphing is also not Borel, not measurable, complete garbage. And we don't want to deal with those. We want Borel graphings. That's where the essence is. That's where the difficulty is. And turns out that, in fact, not every equivalence relation admits a treeing, and very few do. So I'll give you examples. If you close your eyes and put your finger on an equivalence relation, it probably won't be treeable. This is what I'm saying. It's very few of them do. But it's still a big class. Very few do, but if you're working in that area, it looks pretty big to you. So as I said, not every equivalence relation is mu treeable. We cannot choose a point from each class. Here are some examples of treeable equivalence relations. So any orbit equivalence relation induced by the following, the free actions of the following groups are treeable. If you have free groups, they sure induce a treeable equivalence relation. Why? Because what is the Cayley graph of F2 or Fn? It's a tree, right? It's for F2, it's a four regular tree. And so on. So when, say, this F2, so you think of F2 as generated by generators AB. So F2 acts on X. You can now, and this is a Borel action, you can now define a treeing so for the equivalence relation, so E alpha is the orbit equivalence relation, as usual. I want to produce a treeing of E as follows. So we define a T of E, so treeing T of E, by I set T, now I have this huge probability space, it's the 0, 1 interval. I have points x, y, I'm going to tell you when am I going to put an edge and when I won't. So I put an edge between x, y, if and only if one of the generators of the free group, when I multiply it by x, I get 1, or vice versa. So there exists, let's call this plus minus 1. So there are 4 generators, and let's call this set x. So I'm saying there exists a group element in the generating set such that gamma.x equals 1. This is a Borel definition. So T is a Borel graph. What it is, if the action is free, it's like you take this Cayley graph and put it on every orbit. And you can put it starting from any point by homogeneity and the equivariance of the action. It's going to be the same graph no matter which point you started with, so there is no axiom of choice here. Here is the definition, literally. So I didn't have to choose anything. So basically every equivalence class would literally look like this, like a Cayley graph. Very nice. So these are actions of free groups, free actions of free groups. Similar argument you can do for free products of small groups, of finite groups. So that's that. There are other groups like virtually free groups, meaning a group that admits a finite index free subgroup. For instance, GL2Z is such a group. It admits a finite index free subgroup. So actions of these groups are treeable. This is a hard result. A more recent result by Conley, Gaboriau, Marx, and Tucker-Drop is that surface groups, which are the fundamental groups of surfaces, are also treeable. This is another hard result, and the proof is quite beautiful. And then this is even more recent by the same authors, showing that elementary free groups are, again, produce treeable equivalence relations. So what are elementary free groups? They are related to this Tarski problem. It's elementary equivalent to free groups in the sense of first order logic. But you know, if I give you one such group, you would have no idea that is one of those. So they look very different from free groups. All right, however, and here are some examples of non-treeable. So non-treeable equivalence relations, it's a result of Adams and Spazier that infinite Kazhdan groups, or also known as groups with property T, when they're free PMP actions, in fact induce non-treeable equivalence relations. So the GL3NZ as opposed to GL2Z is not treeable. When it acts, it induces a non-treeable equivalence relation. And in general, these treeable equivalence relations don't behave well. If you take product of two treeable equivalence relations, you get something that's not treeable. I'll mention a crazy open problem in the end if I have time. That really bothers me. All right, so these are just sort of picture treeable equivalence relation, non-treeable. There is much more, but I deliberately didn't put it. So now back to.
Are they closed under free products?
Yes, free products are okay, but commutative products are not.
Amalgamated products, maybe?
Depends on what you're amalgamating
Okay.
over. Well, over finite groups you'll be okay. Yeah. All right, so back to the question. Remember, we wanted to calculate cost, and we wanted this cost to carry some information about my action, to remember some information about my action. So this is an easy result of Gaboriau, that if you do achieve cost, then if a graphing of an equivalence relation happens to achieve cost, then it's in fact a tree. There cannot be any cycles. I mean, why is it the case? Intuitively, if there were cycles, you would cut them and reduce the cost. You would remove some edges and reduce the cost. And that's what you do. But you have to do it in a Borel fashion. So if you have non-null many cycles, you can get a Borel disjoint collection of those and then cut each of them in a Borel way to reduce the cost. Okay. But even when, so we know that if we achieve the cost, we must be treeable. The question is the opposite. If we are treeable, like produced by an action of F2 and F3, which is the question we're interested in. So if we are treeable, what is the cost then? Is the cost the same as the cost of a given treeing? So for instance, if someone tells me that E is treeable, it is still conceivable that I can produce maybe two different trees for it, one bushier than another, and so one would have a bigger cost than the other. For instance, this picture. I mean, you know, every equivalence class is just a countable set, right? So who says I can't put a, 5 regular treeing, that's Borel, and a 3 regular treeing on the same equivalence relation? And so then, you know, so the cost of this would be what, 5 over 2? The cost of this would be 3 over 2. So they would give different costs. So this is conceivable, but fortunately not the case. So this is what I would call the fundamental theorem of cost, is due to Gaboriau, and this is what exploded this theory. if you have a PMP equivalence relation and T is a tring, then as a matter of fact, the cost of this one tring is the cost of E. So in particular, if you have two different trings, they have to have the same cost. So it can't be 5 over 2 and 3 over 2 like in this picture. So two different trings give the same cost. This is the content of the theorem. Now, this theorem resolves our question of the talk that I started with. It says that, if now you take an orbit equivalence relation of a free action of the free group on n generators. So on n generators, on two generators, it has cost 2, right? I have to take the degree, which is 4 divided by 2. On n generators, the degree is 2n. I divide by 2, I get n. So any free action of a free group has cost, free group Fn has cost n. That's the corollary from that theorem. But this answers our question. Our question was, if free ergodic PMP actions of Fn and Fm have the same equivalence relation, must n be equal to m? The answer is yes, because the costs have to be equal. And the cost of one is n, the cost of the other is m, so they must be equal. So this is how that very basic question that you read and you're like, come on, let's answer this. I mean, it gets resolved via this nice slick theory of attaching the cost via graphings. So this is the answer. Now, several years later, just to squeeze in my result into the talk, so several years later, after this result, Greg Hjort, who was a professor at UCLA where I was a grad student, obtained a striking converse to this corollary. So what does the corollary say? It says that if Fn acts in a free PMP manner, the equivalence relation then is treeable because you see the treeing, and it has cost n. Greg Hjort obtained the converse of this. It says that if you give me a PMP ergodic equivalence relation that is treeable and has cost n, then in fact I can produce a free PMP action of Fn that induces exactly E. So the picture is the following. You give some abstract equivalence relation with Borel string on it, so these are trees, and you say that the cost of this string is, say, 2. Then Greg Hjort comes, rewires these trees, makes them into amazingly nice calligraphs, and says that, so I can turn any abstract Borel string into labeled, directed, nice Borel collection of calligraphs. So this is for cost, the picture is for cost 2, but he does it for cost n, any cost. So any abstract treeable equivalence relation, as long as it has integer cost, it is in fact produced by a free action of the free group on n generators. So then these randomly looking strings can be transformed into nice calligraphs. So now so this is joint work with Ben Miller, what I'm about to tell you. So what's our contribution to this? We prove a strengthening of this result, which I claim is already strong. But what's the strengthening? So to tell you what's the strengthening, I need to, for a second, I started 6 minutes early, remember? So I need to explain to you what ergodicity for one automorphism means. And I mean, if nothing, it's nice to learn. What I'm about to say is called the pointwise ergodic theorem or the Birkhoff ergodic theorem. If you remember nothing from my talk but just this theorem, I think it's a win. Because this is one of the most important theorems in the 20th century. Now for a second, consider a PMP action of Z. Ergodicity, by definition, is a global condition. You say no measurable invariant set. Every measurable invariant set is either null or co-null. So this theorem characterizes this global property of ergodicity via local combinatorics of the orbits. So local statistical data on the orbits. So what does the theorem say? So an action of Z, a PMP action of Z, is ergodic if and only if, so it's indecomposable, if and only if for each test function you take, integrable, f, if you just look at basically almost every point, x, and look at the finite window around x produced by the action of Z, so take the interval 0, n, and multiply that interval by x, so it's an action, you get finitely many points. And take the average of the values of the function, this function, on these finitely many points, so this is my notation for the average, right? These are like 7 points, so you're taking the average of those 7 points, of the values of the function. Now, as n grows, what the limit is in fact the global space-wise average of the function. So you see, for each fixed point, there are only countably many points featured here, countably many values of f. These, to integrate, you need all the values of f, all continuum many. All of a sudden, these countably many values do capture this value. So this is like a local global correspondence, okay? So this is and this happens for almost every x. So this is the Birkhoff ergodic, pointwise ergodic theorem. Then the picture is the following, for almost every point x, if you compute bigger and bigger intervals, or averages on bigger and bigger intervals, these are orbits of the action. Then this number you eventually get in the limit is in fact the global expectation of f. So this is the Birkhoff ergodic theorem. Now what's our strengthening of Greg's theorem, Greg-Yort's theorem? So remember, this is Greg-Yort's theorem. I haven't added anything. It says that a PMP ergodic equivalence relation E is treeable and has cost n. Then it is in fact induced by an action of Fn, free action of Fn. So you take these trees and you rearrange them into nice Cayley graphs in a Borel fashion. Okay, so that's what Greg does. Now what do Ben and I add to this picture? We add that such that each of the free n standard generators of the free group alone acts ergodically. So not only do we have nice Cayley graphs, but in each cardinal direction of the Cayley graph, the ergodic theorem holds. You see the correct averages as you go. So, besides sort of arranging these graphs combinatorially, I also make sure that they capture the space statistically in every cardinal direction. This is what we prove. I mean, I guess I'll just say that. In other words, given a treeing T, this abstract treeing T of E, we modify it into a different treeing, which decomposes into Z lines with correct ergodic averages for each L1 function. That's what we do. And to do so, besides the result, I was also excited about the proof, because the proof introduced new techniques that I didn't know before. I mean, I didn't know before, but I guess these were just new. So it introduced the technique of edge sliding. So the way you transform these guys into these guys, you try to not break connectivity and not introduce new cycles. So what you do is you slide edges along other edges so that you don't break connectivity. And this sliding has to be done in a Borel fashion. Another thing is we introduce new technique of building finite sub-equivalence relations called saturation and packing. And also we introduce an easy method of exploiting non-amenability. This is very easy, but somehow very useful, because amenability is an awesome condition. It says something exists. Non-amenability is a bad condition. It says something does not exist. So how do you exploit non-amenability? And we give a nice characterization of that. That is, says it's non-amenable if something else exists. So that's good. An edge sliding, so what is an edge sliding that we defined? So an edge sliding along a railway R, by a railway I just mean a set of edges, okay, nothing fancy, just a set of edges, is a Borel map from the set of edges, from all the set of edges to set of edges that keeps the edges of R fixed, so it doesn't move the railway. And for every edge E, so for every edge E, it slides E along, these are edges of R. So it slides E along the edges of R, using them as a railway, into its image. So this is a edge sliding. What we need is iterated edge sliding. We need to keep doing this over and over again. So iterated edge sliding, without even reading this, I can define it for you like as a cartoon. I've seen it in cartoons, in fact, maybe in DuckTales. You know, the way people build railways, you know, from, let's say, across America. If you start from one side, you build some small part of your railway, and then you transport new rails on a railway that you built all over the end of the railway, and then you unload your rails, and you build more, and then you keep doing this. So this is iterated edge sliding, and the iteration goes over a countable ordinal. So, and this way, what it ensures is that if you start with a string, this technique of edge sliding, it modifies the graph without introducing new cycles and without breaking connectivity, which is what we want. So what we do is we take these abstract strings and edge slide them a bunch and turn them into these nice Cayley graphs with correct ergodic averages. So what remains is all of the proof, but what remains is to build z-lines with correct ergodic averages. So partition the graph into z-lines with correct ergodic averages, but maybe that's a story for another talk. And this is thank you in Armenian. So it's a very long word, and we don't say it, and that's why we're moved.
So how do you pronounce it?
Shnorakalutsin.
Okay, I understand.
And which direction do you read?
Left to right.
Yeah.
All right.
All right.